There we go. Okay. Good morning, afternoon, day, whenever it may happen to be. Ladies and gentlemen, this video is for the first section of Unit 3. Now, once again, I do have the notes pulled up over here, so, I can't see this side of my screen over there, so I'm just going to be hanging out over here. So, this video is going over modern atomic theory, which I'm going to be quite frequently abbreviating as MAT. Because modern atomic theory takes forever to say and type. So, MAT. Modern atomic theory, or MAT, is basically just a discussion of what do we think the atom looks like. We kind of introduced some of this when we were going through history of the atom, when we talked about all the different models of the atom. And we're going to be kind of talking about a blend between the Bohr model and Schrodinger's model. That's the planetary model and the quantum model. We're going to use the terms from the quantum model, but we're going to be drawing diagrams that look mostly like Bohr's planetary model of the atom. Okay, so first off, you really have to get into your head just how small an atom really is, because we're going to be talking about things that are way, way smaller than atoms. So you first have to understand how small an atom is before you can really grasp just how infinitesimally small some of these other things are. So let's start there. Okay? How many of you, or I want you to imagine, since I can't get feedback in the video, I want you to imagine for a moment that you have a gum wrapper. Maybe you actually do, and you can do this. Pause this video and try this if you haven't done this before. If you have a normal gum wrapper, not one of those pocket packs with like Trident or Extra or whatever, but just a regular pack of gum, if you take the gum out, the wrapper has kind of a foil backing with a wax paper on the other side. You can carefully peel that metal foil off the back. Okay, and it's really, really thin. Like it's really, really thin. It's thicker on some of those other kinds of gum that I was talking about, the pocket packs. But the regular sticks of gum, the metal foil on the back is very, very thin. Now I'm not talking about the width or the height or the length. I'm talking about the actual thickness of the foil. Okay? That super thin gum wrapper is about 10,000 atoms thick. And now picture it, or get one. If you got one, go get one. It's so extremely thin. And that is 10,000 atoms stacked on top of each other. 1, 2, 3, 4, 5, 10,000. That's how many atoms it takes to get a metal that thick. And it's still so incredibly thin. Okay, so remember that. That's how small we're talking. That small. That's how small atoms are. Okay, so the atom, if we blow one up to be about to a reasonable size, I need to get my whiteboard. Hang on a second. Let me pause this. And I'm back. Better illuminated. So this here is going to be our atom. Okay, so if you imagine this to be our atom, we've blown it up quite a bit, so it's a little bigger than it was. The atom can be broken up into two regions. The nucleus, which you've already heard about, Rutherford, and the electron cloud. Now, the electron cloud is the modern day term. The idea of the electron cloud comes from the quantum model, but our discussion of it is going to look a lot more like Bohr's model. This is what I was talking about earlier. So, at the center of the atom, we have our sun, which is the nucleus. Okay, and it is so very, 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 very much smaller than the atom. Okay, if we're being completely honest, that little dot that I have there is way too big. Okay, the nucleus is far, far smaller in an atom that was blown up to this size. If you were to imagine a atom the size of a baseball field, okay, hydrogen atom blown up to be the size of a baseball field. Okay, the electron shell extends from the outermost fence on the outfield all the way across. The nucleus in that atom would be the size of a dime sitting on the pitcher's mound. Okay, that's how small the nucleus is compared to the rest of the atom. That's why we say it is a small, dense mass concentrated in the center of the atom. The nucleus is way smaller than this. Okay, so the nucleus is small. Already said that. That is not an N. The nucleus is small, relatively small. It is dense, and it is positively charged. Okay, so it's small, it's dense, it's positively charged. Or another way to say that is it's small, it has a high density, and its charge is positive. Okay, everything else is the electron cloud. Every aspect or iota of space in the atom that is not the nucleus is the electron cloud. So the entire thing, except for that, is the electron cloud. And that is all space where you can find electrons. So the electron cloud, which I am going to abbreviate electron as E minus, we'll come to that here in a second. The electron cloud is, again, relatively large. It's most of the atom. It is not dense. It has a very low density. And while the nucleus has a positive charge, the electron cloud has a negative charge. That is an N, charge. Okay, they are opposites of each other. Where one is small, the other is large. Where one has a high density, the other has a low density. And where one is positive, the other one is negative. They're opposites. And that has to do mostly with the stuff that's in them and what is found in those two different regions, which we'll talk about next. Sorry, I had to sneeze, and this time I found the pause button. All right. So those are your two regions. Now, those two regions contain three different particles. I'm running ahead. There is one other thing I need to tell you. 99.9999999999999% of the mass of the atom is in the nucleus. There's like a very, 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 very tiny amount of mass that can be found in the electron cloud. But well over 99% of its mass is in the nucleus. Likewise, when it comes to volume, 99.9999999999999, however many nines you want to throw on there, of percent of the volume is in the electron cloud. In that infinitesimally small 0.000 whatever one left over is the nucleus. Because the nucleus is, as we said, very, very small, but very, very dense. Whereas the electron cloud is very, very large compared to the rest of the atom, but has a very low density. There's not much in it. It is mostly empty space. Now let's talk about those three particles. Okay, the three particles that we talk about when we're looking at atoms are protons, neutrons, and electrons. See if I can make this fit. Okay, these are the three particles that you're going to have to know. Protons, neutrons, and electrons. Now, protons are positive. They have a positive charge, and they are found in the nucleus. Okay, and they have a function. Every one of these has a critical function that you must know. For protons, you should already know this one. For protons, the number of protons is unique for every element. Okay, it is unique for every element. I'm not writing that down because it would take me forever to try to write sideways like this. Okay, the number of protons of these is unique for every element. What do we call that? What do we call that number? It's the atomic number. The atomic number is the number of protons. That is the defining characteristic of an element, is the fact that it has to have however many protons. That is what makes it that element. Hydrogen is only hydrogen if it has one and only one proton. Helium is only helium if it has two. And lithium can only be lithium if it has three. If lithium loses a proton, it's no longer lithium. It's helium. If hydrogen gains a proton, it's no longer hydrogen. It's now helium. Because the definition of helium is 2 protons. The definition of hydrogen is 1 proton. And the definition of lithium is 3 protons. That is how we define the elements. If the number of protons changes, then the element changes. And that can happen, but not with anything we're going to discuss in this class. But you do need to know that. Okay? So protons are positive, they're found in the nucleus, and they're the number of protons is unique for every element. This defines the identity of an element. Oh, and it has a symbol that you're going to see from time to time. It is a lowercase p with an exponent plus sign. Okay? Now, let's talk about the neutron. Okay? The neutron is neutral. It has no charge. I'm going to put a 0, but you could write neutral. You can say no charge, whatever. As long as you know that the charge of a neutron is neutral. It has no charge. 0 works because that is neutral in terms of math, is 0. It is also found in the nucleus. And it also has a specific function that it fulfills within the nucleus. You see, if you thought about this for just maybe even a fraction of a second, you might have come to the conclusion of, wait, if these are all positive, how can they all hang out in the nucleus together? How can we take a bunch of positive things and pack them into a space so unimaginably small and then put them in a space even smaller than that in the nucleus? How will they stay together? Well, there is a force called the strong nuclear force that keeps them together. But it's not enough to make them stay there. Neutrons serve to keep the protons separated from each other. Because if protons actually touch, they kind of repel each other so bad that they explode and fly apart, and the atom breaks down. So protons can't actually be alone in the nucleus. They have to have neutrons too in order to stabilize them. That's why there is always at least, except for hydrogen, there is always at least the same number of neutrons as there is protons. Usually, there are more neutrons than protons. And that is so that these little ball bearings with the plus sign on them, they stay just far enough away from the other ball bearings with pluses on them, because all the neutral ones fill in the spaces between and keep them apart. Okay? So neutrons are neutral. They are found in the nucleus, and their function is to keep these from getting too close to each other. So what they actually do, this is the definition you have to know, they stabilize the nucleus. They keep it from exploding because these don't like each other. They hate each other, in fact. They want nothing more than to run away from each other. But they can't because the neutrons stabilize the nucleus. And since it's stable, the protons are willing to put up with each other. It's kind of like in a seating chart. Two people who just hate each other and don't like each other and don't want to talk to each other. If there's someone between them, they can usually get along by pretending that the other person isn't there. So the neutrons are the guys in the middle who are there to keep the aggressive people from going after each other. These also have a symbol, an abbreviation, like proton has P+. Neutron is, again, a lowercase, but this time an N and an exponent of 0. Now, I put a slash through my zeros. You do not have to do that. I don't care. If you just have N with a 0 without the slash, that's fine, as long as you know that it's N with a 0 as an exponent. Now, let's see if I can do this. Okay, so now let's talk about electrons. Electrons are the wild childs of the atom. Okay, these things actually move around. Both of these are trapped in the nucleus. They cannot move. They sit there, they hang out, and they chill. Neutrons are just like, hey guys, let's calm down. Stabilize. There is nothing to do that for the electrons. The electrons are like your ADHD, hyperactive younger brother, hyped up on caffeine, running around all over the place. They are crazy. They are constantly in motion, sprinting around the track that they are stuck in. Okay? They're constantly on the move. Okay? But they also have a negative charge. And it should hopefully not come as an enormous surprise that they are not in the nucleus, but rather in the electron cloud. By the way, if you haven't figured this out yet, that's the abbreviation for electron. That's the symbol for electron. I think I've used it before. But yeah, that's the symbol for electron. So these things are constantly on the move. In the electron cloud, they're sprinting around this thing faster than you can possibly imagine. Okay? In a space smaller than you can possibly imagine. They are running laps, just constantly moving, because they are where the energy is. Okay? Electrons are full of energy, and they are so desperate to just run around and release it. Okay? So they're constantly on the move. Okay? Those electrons are what actually form bonds. They are actually capable of leaving the atom. The protons and the neutrons are trapped in the center, in the nucleus. They can't go anywhere. But the electrons, which are sprinting around the nucleus, orbiting way, way faster than any planet goes around the sun, can actually leave. And when they do, one way or another, we'll talk more about how this works in the next unit, but when they leave, they form bonds. That is how bonds are formed. So electrons are capable of leaving the atom and forming bonds. And that's their unique thing. So protons are the unique identifier. It's unique for every element. Neutrons stabilize the nucleus, and electrons allow bonds to form. And we're going to spend a lot of time talking about these three particles, protons, neutrons, and electrons. This entire unit is about the properties that these three particles introduce to atoms. And I'm going to go ahead and tell you that the number of protons dictates solely what properties an element is going to have. It's why we use it to define the element. Because when the number of protons changes, the properties of the atom will change. Neutrons can have some limited effect, but that has more to do with when there's too many of them, the nucleus is just as unstable as when there's too few. Okay? Too much of a good thing is no longer a good thing. You eat too much sugar, you're going to get sick. That's what happens when atoms have too many neutrons. Okay? So, and then the electrons, obviously, like I said, are just insane and running around. Now, I need to pause this so I can look up what the name of the worksheet is. It's probably 3.1, but let me check. It is. Okay, worksheet 3.1 is the assignment that follows up this video. If you are not at school for whatever reason, then you can find this in Canvas. Okay, find Unit 3, scroll down to Worksheets in Unit 3, don't go to another module. In Unit 3, Worksheet 3.1, MAT Summary, and fill that in on both sides. So for the symbols, looking at the front right now, the symbols are just write down what the symbols are. The charge, is it positive, is it negative, is it neutral, which one's which? The region, which of the two regions do you find it in, and what is significant about each particle? Okay, I went over all of those in the notes. You have to know those. Memorize that information. It is important. On the black side of that worksheet is the same basic idea, but for the two regions of the atom. So, what particles are present in each region? You should know that. What is the charge of each region? What's the size? Here, big or small. One's big, one's small. What's the density? One is high, one is low. Which one's which? And that's pretty much it. So go through, fill that out using this video. This video is 22 minutes right now, so I'm going to go ahead and stop. It's been a great night. Have a wonderful day, and I will see y'all next time. Thank you.